So just to introduce myself, my name is Mike Holterman. I am key account, global projects, and Flare IQ commercial leader for Panametric. I'm out of Houston. That's right. I mentioned we got a factory that's in Boston area. When I say Boston, it sounds better than St. Billerica, Massachusetts. Just like we have a great place in Shannon Island, but we tell people it's near Limerick. That sounds a lot better as well. But we manufacture, flare flow meters, ultrasonic meters, moisture sensors, and then we get into the Flare IQ, which is what we're going to talk about today, which is a control algorithm software. Just so you're aware, if you're not, we're not going to get into the flare flow meters on this in this presentation, but at 4 o'clock for the next one, I'll be down at 4:16 doing flare flow meters as well. So we're all here at the 4C conference. We are doing a lot of things in our industry for methane. That's the big thing for the last several years, and it's going to continue to be a big thing. The question is, when it comes to flares, do you know what's going on inside your flare system? The answer is, we know more today than what we did 5 years ago, but do we know enough at this point? Methane has got a massive significance when it comes to CO2 equivalent. I'm not going to get into this too much, but there are, there's obviously COP26, COP27, there's been a lot of environmental pledges that countries have made and have lots of aggressive targets. We hear things like 50% reduction by 2030, CO2 equivalent, elimination of flares, routine flaring, all of that. We hear all those buzzwords, but, how do we get there is, I think, the question that the industry faces. We all know that flaring is a source of methane, uncombusted hydrocarbons. Getting into the atmosphere, is a very significant effect of flaring. Downstream, midstream, upstream, all have unique challenges when it comes to flaring. But what it comes down to is we all want construction efficiency to be around 98%. That's the goal of industry. A lot of facilities are below that, a lot of facilities are above that. So it's about getting them all to that level. Now, there's always the question that, we always like to pose questions here. I'm asking you as all a question, and I'm hoping that you're going to ask me questions as we go through this. But what if you can monitor, reduce, and control your emissions associated with flaring? We ask these questions when we're going around to large oil and gas energy companies with their executive groups and that sort of thing, that aren't environmental questions. Everyone here, you ask yourself these questions in your careers, right? But often you go to executives and they've never really pondered this sort of question. So it's a filler slide basically to lead you to this Flare IQ. And I'll get into this as to what Flare IQ does, how it works, and that sort of thing. But the key is that we do our best to optimize your system. Okay? And if I'm talking too fast, if I go over something that you want to come back to, please stop me. This is, I can stand up here for hours and hours and hours and talk about this, but if it's not answering your questions, it's no use. Okay? Why Panametrics? Well, as Fred mentioned, Panametrics is very proud of our ultrasonic flare flow technology. We invented it with ExxonMobil in Baytown in 1984 is when we sold our first commercial one, but it's a 4-year program where we created the ultrasonic flow meter. So, and we've been leading the field for the last 40 years. Okay. Challenges of measuring flares. Everyone who deals with flares knows these challenges. When things are running fine, nice and slow, very little flow going through there. You have to be accurate, below 1 foot per second going through a line. When you think of that, that's not much flow. But also in a emergency situation, these things need to evacuate the entire plant. They are ultimately safety devices. We're all here for environmental. Let's be clear. Flaring, routine flaring, emergency flaring, all that, it's a safety device. So they're not going away entirely. We have there's all these different things, but one of the things that comes in is a wide temperature range, but also a the composition of the gas going through there can change significantly quickly. You need to have a technology that's going to be able to handle all those changes. So this is for your reading pleasure after it's posted. Put a glossary of terms. Some of these are going to be familiar to you if you're a measurement person. Some will be familiar to you if you're an environmental person. If you're both and you know all these, that's awesome. Yeah, if I use one of these and you don't know what it is, please ask me and I'll slow down. The big one right now facing us is the difference between combustion efficiency and destruction and removal efficiency. They're both used almost interchangeably. I don't know if this has been covered under in any other section. I try to simplify things down. When you have combustion, that didn't work out well. When you have combustion, you have a hydrocarbon plus oxygen. That's obviously the source of ignition, burning. You're going to get a mix of complete combustion, CO2, incomplete combustion, the carbon monoxide, water, and you're going to get soot. So ash, carbon coming through there. Obviously, 98% combustion efficiency means it's going to 98% CO2. But there's other things in there too. So when you're talking combustion efficiency, it's CO2 only as a percentage, of the entire amount. Destruction removal efficiency is carbon dioxide plus carbon monoxide and soot. This is why destruction removal efficiency is always higher than the combustion efficiency. The RSR rule calls for 96.5% combustion efficiency for 98% destruction removal efficiency. So just industry is moving towards DRE because I was in a couple meetings with a company in Europe where I think they had this many people in the room and I think this many people were PhDs and me. And they were talking about, the physics behind incomplete combustion, how it's, not getting the proper number. And this is why they wanted DRE. So people much smarter than me prefer DRE. So that's what we're going with. So all that to get to what a typical flare system is. Okay. Very busy slide. I think we've all been around facilities. We all know that you've got your process units here. You got flare laterals going through hopefully some sort of flare gas recovery system. Most facilities are either looking at putting that in or have put that in. And you got your knockout pot to the flare system. Now I'll get into a little bit these dotted lines because there's a couple different types of flare. Now, just to get a show of hands, folks who are in the downstream space, petrochemical or refining. Okay, anyone in midstream? Anyone in upstream? So the second half of my presentation is going to be really boring for you guys. No problem, but it's still an important part. So in the downstream space, you'll have assists on your flares. And I don't know if there's there we go. There's assists, whether it's steam or air. Some places use gas, but usually in refineries, steam, because you've got a lot more infrastructure there. That steam line it does a number of things, but once again, to put it down to my level of understanding, it really promotes mixing inside that flare stack, weighs that flare gas down, and it allows the gas to stay in the combustion zone for longer. The longer the gas stays in the combustion zone, the higher the combustion rate. So the idea is, if all of a sudden you're running 200 feet per second through that flare line, you got to put a lot of steam in there to weigh it down so it stays in the burning stage for longer. Okay. Obviously, there's the pilot flame tip. There's been a number of presentations here talking about pilot flames. So I won't get into that, but it's a whole different world. And in the center of it all is your DCX, distributed control system. Number of manufacturers in that, obviously Emerson, Yokogawa, Honeywell, lots of those. Okay. This is where Flare IQ comes in. So this is more of a schematic version of what I just showed you. We've got your flare vent gas line, a fuel gas line, and a steam line. Right here, this is your flare, ultrasonic flare flow meter. Hopefully, it's a Panametrics, but there's a number of manufacturers of that. this BTU analyzer, we put when available, because one of the unique things about North America is most facilities use this. They have either a gas chromatograph or a mass spectrometer. Elsewhere in the world, there's a lot more calorimeters, giving you a bulk BTU number and not the speciated, composition. Okay? This makes the RSR rule a lot more achievable than elsewhere in the world. Okay. Also on here, your fuel gas line, this is how you boost your BTU content. Let's say you have a lot of nitrogen in your line. You need to put some gas in there to get your BTU content above 270, which is the RSR rule. Most places like to keep it above 300. You also have a flow control valve there. Up here is a steam line. You have a steam flow meter. Or if you have an air assist, you'll have a blower, hopefully with a variable frequency drive on there to be able to modulate how much air is going into the line, as well as some sort of valve. What's unique about these is that they all go back to the DCS. So we connect to the DCS. This is where all the information is stored. So we are able to connect directly to the DCS and do a lot of calculations with your raw data. Okay. We take in flare gas flow, steam flow, fuel gas. We take in the data from your gas chromatograph or mass spec, because you're going to have things like nitrogen, CO2, you're going to have C1 through C6, maybe even some vapors of bigger hydrocarbons. And we take that in because that's all going to come down as part of your combustion efficiency. Okay. When you're transmitting this much data, from the DCS, Ethernet over Modbus, or Modbus over Ethernet is really the only way to transfer this quickly. Okay, we're able to work any sort of DCS that you have. I mentioned a couple of manufacturers of DCSs. If you just have a PLC type of setup, we can work with that as well. But it's about getting the data from these three flow meters and this BTU into the unit. Okay. Now, this is where I like to ask a question, and those of you who sat through one of my presentations before, I apologize, but how efficient is your flare? This is determined with your naked eye. Can the operator look at how well your flare is running? I'll give you a hint. When I'm asking what is the most efficient flare, it's not this one. Okay? So just show of hands, who thinks that it's here? This one over here. Got a baby in the back. I that's a conversation starter in the back right there. Then there's this one here. How many? Oh. How about this one here? All right. So this, wow, you guys must be all top line operators then. You're going to be working a control room. The point of this slide is to show that there really isn't much visual difference between 90 and 98% combustion efficiency. Right? And this is where you need to use data to be able to determine that. We can use, cameras. I'm not talking the IR cameras, but like a lot of places have physical, like regular cameras on the flare system, in which the operators look at it and adjust the steam back and forth to be able to optimize the smokeless operation, right? But it's very difficult to tell the difference. This is where you didn't ask which one our neighbors. Which one your neighbors want to see? Oh, I know what they want to see. Yeah, we've been trained as a society. I always laugh when I'm driving down the road, near a pulp mill or whatever, and they got a truckload of wood chip, and the sign saying, "It's not smoke, it's steam." Come out. We've been trained that white smoke is good, black smoke is bad. In flaring, this is the worst possible condition. But it's, we were at a facility starting up a flare IQ, and they went from something between this and the 70. They flipped the flare IQ on and started using the data they was getting. And all of a sudden, it was like this 8 foot high flame. I was standing on the controller, the phone started ringing. The neighbors were calling up, asking, what the hell is going on here? Is the city going to blow up? Type of thing. Now, with that being said, there's a role for our companies to educate side to have community action meetings before you do changes like this, because that's what the neighbors have problems with. So yeah, very good point. So oversteaming, you can read this slide afterwards, but I think that when it comes to why do we oversteam? When you look at the flare, you got a bit of black smoke going off of it. What does the operator do? My dad's a plumber, so he loves the quarter turn ball valves. So I just like crack open that quarter turn ball valve a little bit, let more steam. And how often do you go back and turn that steam down? It becomes, and then you end up with like that picture of a 70%. That's a well-run flare, but it's not. You got a ton of methane, literally tons of methane, escaping into the atmosphere. Okay, so yeah.
One of the examples you're showing look like kind of normal flare venting operation. Do you have a like section around like when the flare events actually occur here?
So I purposely left something off of here. I can get it to you. It's a YouTube link of it's Limo, Ohio. It's on YouTube. It's in the public space where they had flaring, and it's a 3 or 4 minute video, and they had Flare IQ installed. And it started a massive flame, very unorganized flame, and then coming down into like a ball of fire, where the combustion zone is much more, it's tighter. So I can get you that link on YouTube, and I'm at my credits here, but I'll get your information from the sheet, I think, email. Yeah, it's most of the time, this style of flaring is what's happening. Well, so yes, what's happening when a flaring event happens, right? How does it react? So yeah, it's good point. But steaming, as I said, because people see some smoke, turn it on, never turn it off. These are 3 refineries, these are real life scenarios. Okay. I'm only focused on refinery 1, so I think it's more of a regular type of thing that you'll see. So they were using 3,300 kilograms per hour of steam, and it's all metric units here because we did this talk in Europe too long ago, and I like the size of this graph. But 3,300 kilograms per hour. I guess that's probably about 7,000 pounds per hour of steam. They went down after Flare IQ to 350 kilos per hour. A 90% reduction of steam. All that it was given them, it was 86% combustion. Still not that bad. They had a healthy looking flame. But after Flare IQ, with that little bit less, they got around 98% combustion efficiency. And when it comes to, we're all subject to cost factors in our facilities, right? Costs are always a big thing. Compliance costs money. Well, this site, over the course of a year, we're saving 605,000 euros, so around $600,000 a year in steam. Now, I'm a sales guy. I don't agree with how they calculated this. Probably more like 400,000. We like to make things look good. But it's, in all honesty, like steam costs money. Whether it's $3 per 1,000 pounds to generate or 6,000, everyone's got a number. Your powerhouse engineers will know what that is, and we calculate that out. In a world where carbon credits are going to become a thing, it's also, a large amount of savings by optimizing your flare. This is not even talking about the makeup gas, the fuel gas you're having to add to compensate for oversteaming. As you add more steam, your BTU content drops. You got to add more gas. So it comes down to, for me, reduce the steam, reduce costs, and become compliant. There's not many self-funding compliance efforts, in our industry. Usually environmental work, it costs money to run a refinery. We've seen this site here funded their entire RSR program through these savings. So it's just something to remember that very rarely you can save money by doing the right thing. So take advantage of it when you can. How do we do this? How do we optimize the steam? What Flare IQ does is the steam to vent gas ratio. Most facilities, when you're in manual control, it's for every 1 pound of steam or of vent gas, put 1 pound of steam. Yeah, 1-to-1 ratio. If you're running pure methane through there, you don't need that to be one, you can do half a pound of steam. Or if you've got some strong double bonds actually going through the line, you're gonna wanna have maybe 2 or 3 pounds of steam to avoid smoke. But it's about optimizing that. So ours and some aspects of ours are very easy to meet. 270 BTU%, no problem. Jackson gas through there, perfect. But the smokeless flame, smokeless operation is a hard one to maintain. So this is how we do it with Flare IQ. We have a dynamic steam to vent gas ratio. Okay. Here's the logic in here, presenting controls people.
Yeah, but just in order to get that, you have to have electric lights or whatever.
No, so in the most ideal way is, so the flare flow meter provides an average molecular rate going through your line, right? However, when you're going and you're calculating BTU content, you need to strip out the inerts because nitrogen and ethylene are the same molecular weight. The flare flow meter is going to tell you that. Goes in the average thing. So if you take your output from your BTU or from your GC, strip out the nitrogen, all of a sudden you've got a pure hydrocarbon. When you have a pure hydrocarbon molecular weight, it's a pretty straightforward API chart that goes over to BTU.
I guess just to be specific, if you don't have GC on this, but you have calorie system.
We can operate with a calorie. However, you need to manually input the amount of inerts. If you average around say 10% nitrogen, then we'll put that in, and we fairly closely use that. So for upstream facility where there is no infrastructure upper midstream, and I'll get into that a little bit. It's all the work that we're doing on that, but you can work with the calories, just not ideal. So my colleague Victor Tafoya did his presentation earlier on digital verification of flares using Flare IQ. And for that, we need to have a proper composition to be able to do that. But for the control scheme, we ask for chromatograph or calorimeter. Okay. And if you don't have all of these in your BC column, that's okay too. The more you have, the better. We can do it with less. Basically, what this eye chart is telling you is that take a bunch of inputs from your system, add the GC or mass spec data, and we will give you the proper amount of steam, the proper amount of fuel, and then calculate your max velocity. So it all goes through your DCS. We provide the amount of steam. It's your DCS that feeds that information to your control valve. We are not a control valve or a control systems company. We're an information company. And what does that mean to a refiner? This is a real world case within 2020, but we tried to look back as much as we could. But the orange or the blue line is what was traditionally steam rates. Orange line is what we did after Flare IQ. So if you look at the years, 20,000, 8,000, 30,000, 100,000. These numbers for refiners, you're running an oil refinery, even $100,000 a year is not going to move the needle. We recognize that. But if $100,000 plus compliance, that's worth looking at. Okay. We always talk about future carbon tax. I think we all know that eventually they're coming. How it's put in place, we don't know yet, but they're already having them in Europe and Canada and China. We got carbon taxes in place. So that's our story on downstream. Now we've got half the time left, and then move a little bit more to the honest system. These are some of your ones that don't have the infrastructure. Maybe you're running air through the line. Talk about what we're doing, and then I want to talk very briefly about some data that we're really looking forward to being able to publish in the next month or two. And that, I think, can be a game changer for the industry. Okay. So first off, We call this CE, so combustion efficiency and PEM. You've probably been to a number of sessions where they talk about PEMs. Every company has got their own definition of what PEMs is. And on the next slide, I'll get through to, what our version is. Predictive emissions measurement system. But when it comes to methane, I mentioned we need to have a much better idea of what's going to happen at the flare tip. Okay. What we started with, so our sister company within Baker Hughes is called Bentley, Nevada. They do a lot of rotating equipment, monitoring a lot of critical turbines, and they have software packages that are already on the site. So we adapted our CEM solution, Flare IQ solutions into System 1. Because most of these facilities already have the software, you need more software. Just add on what they call an insight pack. However, Flare IQ as a standalone system, we needed to develop that. So just as of late last year, we've been able to get that, and we've actually, sold, several of them standalone versions into Egypt and Latin America. This is a stripped down version. There's no control factor. On an upstream, I'm going to bounce around a little bit because, like I said, this top. An unassisted flare, you got a flow meter and nothing to control. How can we give you optimization when there's nothing there? The flare tip manufacturers do a great job in engineering their flare tips. Most of the time, these types of flares are running very high concentrations of methane. So they can easily say, yes, it's going to be 98% combustion efficiency. And that's great. But as we said, there's other aspects in terms of VRE. So Flare IQ is able to take that data from the ultrasonic flare meter, as well as some other information, and give you real-time combustion efficiency, destruction removal efficiency, CO2, CO, and VOC, and do the resulting calculations of CO2 equivalents. Right? What we're finding, we developed this for the upstream world. I actually talked to more and more refineries. They also want this information. So we can package it with the control algorithm, provide you these outputs along with the control algorithm. I'll get to in a second with the validation. How do we prove our numbers out? Because that's the journey that we're on. Okay. So to that effect, combustion efficiency above the flare tip. Combustion efficiency here is a function of the BTU content in the line, which we get through the flare flow meter, calculations. The exit velocity, so how fast is the gas flowing through the line? Your inert gases, like nitrogens, CO2s, that sort of thing, that don't burn. And what we're finding is more and more important to understand is the cross-sectional winds. We all know, and I tell the story of, when you're a kid and you're around a campfire on a still night, the flame is one way, but on a windy night, the flame is completely different. The cross-sectional winds have got a massive effect on what happens above the flare tip. The flare tip manufacturers do really a job to minimize that, but it still affects. So our results. So this is a facility in the North Sea. I can say it because it's probably that we have partnered with BP in their offshore world. Where we installed Flare IQ on HP and LP flares. The flare tip manufacturer and the number that BP is reporting, is 98%. The static emission factor, regardless of the velocity going through the line or the composition in the line. So these are highly engineered flare tips. They do a great job, but they have to have a static number because of the static device. So when you're measuring Flare IQ and using the data that's going through the line, and this is high methane content gas, which is always in the upstream space, we were actually measuring 99.2, 99.3% combustion efficiency. Great. The flare tip manufacturers, yeah, they're right. 98%. But is it better? And that's important to upstream, compliance. And what that means, when you look at the numbers, going from 98 to 99.3% combustion efficiency, or combustion efficiency. It doesn't seem like a whole lot, 3%. But when you look at those commitments that companies have made, 50% reduction by 2030, that's a 65% reduction in their methane releases through the flares. That solves their 2030 dilemma of how do they reduce.
Paper reductions.
Pardon me?
Paper reductions.
Paper reduction, because they were reporting this, and we're working with them so that they can hopefully be reporting this. It's not there yet. Regulators need to accept it. And so, yeah, so this is where we get to the validation of the results. Very difficult as a manufacturer for us to approach any regulator and say, look, we've got this great solution, you should look at it. You need to have a partner to walk with through this. And so for this, we partnered with BP, and we're needing to do some validation. Now, we had this information from the field. This is the flare IQ versus the mass spectrometer. This is the refinery in the US that provided us with this feedback. Now, I apologize for this, but you know, the red on here is the data from the mass spec. The green is the flare IQ. Now, you know, as it bounces around, you know, it matches within 3 to 5% of the mass spectrometer. Now, they had a flaring event. I love GCs, I love mass spec, but I'm a chemical guy from way back. But these devices, they go into calibration mode. You know, they have to have a regular calibration now and then. They also, you know, if they sense something's wrong, they feel an error, they'll go into calibration mode. That's what happened on this mass spec. Is that they had a massive flaring event. They went from BTU content, you know, 550, all the way up to over 1,200 BTUs per standard cubic foot. That's a big jump in a short amount of time. And the mass spec was like, oh, error mode. I gotta go and calibrate. Okay. Which is fine. That's what they're designed to do. They're, you know, you don't want false alarms. And so it dropped down into calibration mode. The flare IQ kept tracking, and once it came back from calibration mode, it was still 3 to 5% of it. It's field data, not third-party validated. You know, we recognize that. But it gave us a lot of hope to go to third-party validation. So we did this earlier this year, end of January, early February, at John Zink, partnered with BP. This was in Tulsa, Oklahoma. This is a great picture, just to explain a little bit. We had 3 different flare tips that we tested, 3 different flare tip designs. We had this snorkel that had 6 thermocouples on it to ensure that we were gathering, you know, hot post-combusted gas off of there. And it was pulling a sample down to a GC to do it as a comparison. Okay. They set up a proper statistical design. You know, it was going to be 80 cases, high, medium, and low flow, high, medium, and low BTU content using ambient wind. We all know Oklahoma has got lots of variable winds from day to day, and we were there for 2 weeks. You know, so we were going to get different winds. The problem was, I don't know if anyone here is from Oklahoma, but for those 2 weeks were some of the lowest winds that Oklahoma has had, you know, in a long time. So we weren't able to complete all of our cases, but we were able to do enough to get a proper results. And so right now, we just received the results back from John Zink on March 20th. Our team and BP team are going over the results, validating, you know, making sure, you know, and doing a proper analysis of it. And we also did CFD simulations of these. The 48 different cases, we had 22. We've had 22 of the 48 are done. They're being done by NEL of Scotland. And we're going to be, you know, doing a comparison. That's part of the post process. So early results are looking very positive. Can't talk about them yet. It's got probably about a month we'll be able to publish data. And from there, BP and Panametrics, basically, we're going to start to approach the regulators to talk about this as an alternate method of determining the combustion efficiency at the flare. probably, if, the results are as good as what we right now believe they're gonna be, you'll be hearing a lot about this. We're gonna be saying it from the rooftops. We'll be presenting papers along with BP, at different conferences globally. So we're very excited about this. And I think that this is a bit of a game changer when it comes to player IQ acceptance, because the question has always been, yeah, but it doesn't work. And then we explain how it works. How do you know? There's a little bit of doubt around. So we're hoping once this data is released, it'll start to take away some of that doubt. Okay. Oh, hey, look, I didn't even realize there was a video in there. So yeah, so that's how they were working. And when I was there, these thermocouples on this end, they all needed to stay above 600 Fahrenheit in order for it to be considered a proper sample. And so as it moved them, as it dropped below, then they would that data gets dropped. They would run each sample for about 15 minutes. So when it comes to flare IQ, I talked a little bit about panometrics and our history. We do technically fit for purpose solutions. Our CE and destruction and removal, it's not dependent on weather. The IR cameras are a great solution, but they're subject to fog, rain, snow, and that sort of thing. So we do an in situ measure for this. We consider it to be a low-hanging fruit for abatement solution. You already have almost all of this data in place. And just using the data, in a better way. And compared to the cost of putting a flare gas recovery system, it's quite reasonable. OGMP 2.0, there's a couple sessions on that here. We have level 4 compliance, OGMP 2.0. I'm not the expert on that. If you have questions about OGMP 2.0, please let me know. I'll get you in touch with the right people. And then when it comes to the cost effectiveness, I mentioned, $100,000 to a refinery isn't always enough to move the needle. But the cost of this is much less than a lot of other solutions as well. Right? So with that, I powered through it. I know I had a lot of information there. So questions? Yes.
Best student specifications on there, but how does there calculate the combustion efficiency? Is it based on some empirical equations?
Yes and no. So our base measurement is the speed of sound through the flare gas. That you get through the flare meter, airflow meter, through ultrasonically, you're able to determine. We've always been able to do the molecular weight calculation through the flare meter. Pretty good accuracy. From there, we strip out the inerts, which we get that data from the gas chromatograph. And we have a speed of sound of a pure hydrocarbon. API has some charts that are able to go from the molecular weight of a pure hydrocarbon to BTU content. And it's with crazy accuracy that they do that. So that's how we do that. Then we take into account the wind speed, the velocity through the line, how much steam you're putting in. They're calculating that. So base measurement is the speed of sound. Sorry, I did speed over that. That's sorry. Anything else? Anyone else? Yes.
You talked about how the system can strip out nitrogen. What about hydrogen? Doesn't sound.
And yes, and on that, finally, the hydrogen on that API chart, it's the one with the highest error. I think it's like 6% of. So yes, if the GC provides you the hydrogen amount, yes, we can. We actually use that in a bit of a different way because for refinery sector rule and EMAC, hydrogen, it's not a pollutant. So we actually calculate that into your BTU content. So while it burns at 264, I think BTUs, right? We can count at 1,212. So that's another way that we cut down on the cost of the makeup fuel gas. But yes, yeah, we definitely want to pull hydrogen out of that. Sometimes you don't have that on GC, so you lose a little bit of accuracy on that as well if you don't have it. Yes.
We already applied this for in GMT level 4 reporting. But
So looking at the 2.0, right now, it's a self-certifying. So where we are asked for, yes, we provide that, but when it's self-certifying, I have my script, but yes. Okay. And if you're wondering like how many flare IQs we have installed globally, we're over 200 of them. Our partnership with BP alone is over 70 systems are installed and currently operating.
All right, thank you, Michael.
Thank you all.